All right, let's jump right in. Today we're doing a deep dive on CVE 2025-14847, a pretty nasty vulnerability in MongoDB that's earned the nickname MongoBleed. This thing is a critical pre-authentication memory leak. So if you're running a self-hosted MongoDB instance, this isn't just another routine advisory. It's a serious heads up.
And to really get why this is so urgent, you have to look at the numbers. Right now, we're seeing upwards of 194,000 MongoDB instances just sitting out there, wide open on the public internet. And here's the kicker. Because MongoBleed requires zero authentication, every single one of those is a potential victim. This is not some theoretical problem. It's a massive exposed attack surface waiting to be hit.
So here's our game plan for today. First, we're going to define exactly what MongoBleed is. Then, we'll peel back the layers and look at the actual flaw in the code. After that, we'll talk about the real-world impact, how to fix it, and probably, most importantly, what we can all learn from this, whether you're in development or security. Okay, first section. Let's get to the heart of it. What is MongoBleed? This table really tells you everything you need to know at a glance. You see that CVS score? Up to 8.7? That's squarely in the high-severity bucket. But the two lines I want you to really focus on are information disclosure and authentication none. You put those two things together, and you have a recipe for a really bad day. It means an attacker needs absolutely nothing, no username, no password, just a network connection to start pulling sensitive data right out of your server's memory.
So here's the one-sentence summary. An attacker from anywhere in the world sends a very specific, weirdly formed compressed message to a vulnerable MongoDB server. The server's code gets confused trying to decompress it, and when it sends back an error, it accidentally includes raw chunks of its own memory, data that was never, ever supposed to leave the server.
All right, now for the fun part, the technical deep dive. Let's see how this thing actually works under the hood. The bug is buried deep inside MongoDB's network protocol, specifically in how it handles data compression. In this slide right here shows the classic gap between a good intention and a bad outcome. The original idea was actually pretty clever. It was a performance optimization. The client says, hey, I'm sending you some data. When you decompress it, it's going to be exactly this big. The server then pre-allocates a perfectly sized buffer, fast, efficient. The fatal mistake? The server trusted the client's number for allocating memory, but it never double-checked if the actual data matched that number. And here it is. This is ground zero, the OP-compressed network packet. You can see a few fields here, but the only one that really matters for this attack is uncompressed size. That's the part the attacker has complete control over. They can set this to some ridiculously large number like a gigabyte while sending a tiny little payload that's only a few bytes. That mismatch is what breaks everything.
You know, this isn't a new type of bug. It's a classic programming blunder. So common, it has its own classification, CVE-130. It's what happens when a program is told one length, but receives another and just doesn't know how to handle that contradiction. It's a fundamental failure of the golden rule. Never, ever trust user input.
Now, if this whole scenario is giving you a little bit of déjà vu, it should. Conceptually, this is the exact same class of bug as the infamous Heartbleed vulnerability that basically broke the internet back in 2014. In both cases, an attacker sends a small request but lies about its size, tricking the server into sending back a much bigger response filled with whatever happened to be in its memory at the time. This comparison isn't for drama, it's to help you understand the severity here. So let's walk through the full attack, step by step. 1. Attacker connects. No login, nothing. 2. They send that malicious packet with the big lie in the uncompressed size header. 3. The server, bless its heart, believes the lie. It allocates a huge chunk of dirty memory full of leftover data from previous operations. 4. And this is the clever part. MongoDB's data parser, called bson, starts reading. It reads the tiny valid payload and then just keeps on going, right into all that junk memory. And 5. The parser eventually hits something it doesn't understand and crashes. But in the error message it sends back, it helpfully includes what it thought were field names, which is actually the leaked memory. Game over. And believe it or not, this entire vulnerability can be traced back to this single flawed line of logic. When the decompression function was done, it returned output.length. Now, you'd think that means the length of the decompressed data, right? Wrong. In this context, it was returning the size of the entire buffer that was allocated based on the attacker's lie, not the tiny amount of actual data that was written into it. The fix, then, is almost beautifully simple. The patched code ignores the buffer size and instead returns actual size. This is a value that comes directly from the zlib decompression library itself. It's the true number of bytes that were actually written. This one little change makes all the difference. Now, the rest of the code only looks at the real data and never wanders off into that dangerous uninitialized memory. It's a perfect example of how one small logical error can have massive security implications.
So we know how the exploit works, but what's the actual damage? What happens when this gets used in the wild? Let's talk about the fallout.
When we say memory leak, what are we actually talking about? Well, it's pretty much a nightmare scenario. Because the leak comes from general server memory, it can contain literally anything the MongoDB process has touched recently. We're talking API keys, database credentials, AWS session tokens, pieces of other people's database queries, even environment variables from the server itself. For an attacker, it's like hitting the jackpot.
And I want to be crystal clear, this was not some theoretical exercise. A fully working public exploit script dropped on Christmas Day 2025. And as you can imagine, it didn't take long for people to start using it. We have confirmed reports of attackers actively hitting vulnerable internet-facing servers with this exact technique.
The scope of this is huge. It affects pretty much every major version branch for years. But please, everyone, look at that bottom row. Versions 4.2 and older, they are end of life. That means they are vulnerable and they will never get a patch. If you're running one of these, you are just permanently exposed. This is what we mean when we say technical debt is a security liability.
Okay, enough of the doom and gloom. Let's talk about solutions. How do we protect ourselves from this?
You basically have 3 lines of defense, and you should think about them in this order. Number 1, the best and most complete fix is to just upgrade. Get to a patch version and the vulnerability is gone. If for some reason you can't do that right away, there's a workaround. You can disable the specific compression library that has the bug. And finally, number 3, the best practice that would have stopped this attack before it even started. Restrict network access. Your database should not be on the public internet, period. For anyone who needs that immediate workaround, here's exactly how to do it. You can either add it to your config file or pass it as a command line flag when you start the server. All you're doing is telling MongoDB, hey, don't use zlib for compression. The server will just use the other available options like Snappy or zst, which are not vulnerable. This effectively takes the buggy code out of the picture.
All right, let's zoom out. What are the big picture lessons here? What can we learn from MongoBleed that applies to everything else we build and secure?
This timeline tells the story of vulnerability response in the modern era. Look how fast this happens. Patch is already on the 19th. The public advisory comes out on the 24th. The very next day, Christmas, a public exploit is on GitHub. In just 3 days after that, it's already being used in real attacks. The lesson is simple. The gap between disclosure and exploitation is gone. We're talking hours, maybe days, not weeks.
For all the developers watching, this is a masterclass. Lesson 1. Client input is poison. Never trust it, especially for something as critical as memory allocation. 2. When you use a library, trust its return values. Use the actual size it gives you, not the size you hoped for. 3. Know that fast memory allocators don't wipe memory for you. What you leak might be old, sensitive data. And finally, fuzz test your network code, especially anything that runs before authentication. Fuzz it like your job depends on it, because it does. And for the security teams, the takeaways are just as stark. 1. A pre-auth bug is a 5-alarm fire. It's your top patching priority, no questions asked. 2. Your incident response clock starts the second an advisory drops, because the exploit is already being written. 3. Defense in depth is not just a buzzword. A simple firewall rule would have made so many people immune to this. And 4. You have to be ruthless about killing end-of-life software. It is a ticking time bomb in your environment.
And this all brings us to the final, most important question. Yes, patching the CVE is the right tactical move, but MongoBleed should force us all to ask a much bigger, more strategic question about our security posture. Why was the database on the internet in the first place? Fixing this one bug is reactive. Rethinking your network architecture so it can't be reached, that's strategic. And that is the most powerful lesson we can take away from this whole mess.